Okay, so what happens if direct substitution doesn't work? So that's what we're going to focus on this next part. So we're going to try direct substitution. So this says the limit as x approaches -3. So if we wanted to do direct substitution, we would plug in the -3 everywhere there's an x. So if we do that, we're going to end up with 9 minus 12 plus 3 over 9 minus 6 minus 3. So we're going to end up with the 0 in the numerator and 0 in the denominator. Well, it's okay to have 0 in the numerator, but you cannot have 0 in the denominator. So that means that is undefined. Okay, so that does not give you an answer. Okay, so we'll come back to that in a second. So I'm going to do the same thing with this one. It says the limit as x approaches 1 from the left. Well, it doesn't really matter if it's the left or the right. To do direct substitution, you're just going to plug in that number. So we're going to plug in 1. So if you plug in that 1, we're going to end up with 8 over 0. Once again, we have 0 in that denominator, which we can't have. So this is going to be undefined. Okay, so these are instances where direct substitution does not work because you get an answer that's undefined. All right, so we're going to look at graphically what's going on, and then we're going to figure out how we fix it algebraically. So this is review from what we did on the first day. So it says just because a function is undefined at a value of x does not mean that a conclusion cannot be reached about the limit. So we're going to consider this rational function, and we're going to figure out what's going on here before we actually look at the algebra. So using our graph, the limit as x approaches -3, well, here's -3. Remember, you have to check from the left and from the right. Well, it's still approaching that y value of 1/2. Okay, so this will be 1/2. Now, what's going on here? At 1/2, we have a hole. So I want you to look at something. We did the same limit up here algebraically. We tried to do direct substitution, but it didn't work. But see, we can actually get an answer. So that just tells you that there's something else algebraically we can do. So there's a hole there, okay, but there's still a y value of 1/2. Okay, so we'll go back to what that means in a little. And then down here, we want to do the limit as x approaches 1 from the left. So at 1 here, we have a vertical asymptote. If we come in from the left, those y values are getting smaller and smaller, so it's approaching -infinity. And then this one says the limit as x approaches 1 from the right. So we're still at 1. We still have the vertical asymptote, but if we come in from the right, it's getting bigger and bigger, so it's approaching infinity. So here we had vertical asymptote. Now, keep in mind, when you're doing the left and right limits here, you can get an answer. But if I asked you what the limit as x approaches 1 of this f of x here, it would be does not exist, okay? Because remember, you can't, these have to be a real number, okay? So for it to exist, so that doesn't exist. And the reason here is because x equals 1 is a vertical asymptote. Alright, so up here we figured out we can't just do direct substitution. It was undefined. But down here we figured out there's actually answers for this. We had a hole here, but it still had y value, and then here we had the vertical asymptote, so they still had answers. So here's what we're going to do. So it says we'll perform the same algebraic analysis to find the limit of the removable point discontinuities. So what you're going to do first is you're always going to try direct substitution. Now I know I did it up there, but I want to just show you just that way you have it for your notes. So you always try direct substitution first, because it could work, and then that's all you have to do, and you don't have to worry about anything else. Well, we already figured that out there. That was 0 over 0. So you can't use direct substitution. Okay, so you got to come up with another way. So what you're going to do for what this is called the cancellation process. The first step is going to be to factor the numerator and the denominator. So our first step is going to be to factor the numerator and the denominator. So if we factor this, x squared plus 4x plus 3, we can factor that into x plus 1 times x plus 3. And then the denominator we can factor into x plus 3 and x minus 1. So we can cancel out x plus 3. Now, if you remember from pre-calc, when you cancel something out, that means it's a whole. It's a removable point, so it's a whole. So let's just kind of write that. So x equals -3 is a whole, which means it's a removable point of discontinuity. Okay, because you literally removed it. Well, we already know from our graph up here, because this is the graph of this limit that we're trying to find, we already know there was a hole there. So that makes sense, okay? So first step, you're going to factor. You're going to cancel out whatever's in common. Second step, now you're going to set up your limit with just what's left that didn't cancel. So now we're going to have the limit as x approaches -3, and all we had left in the numerator was x plus 1. All we had left in the denominator was x minus 1. Now we get to use direct substitution. Okay, so remember direct substitution, you're just plugging in that x value. So we're going to end up with -2 over -4, which is going to be 1/2. Which is exactly what we got up here when we looked at the graph. Okay, so you're going to try to do direct substitution first. If it doesn't work, then your next step is going to be, okay, can I factor? So if you can factor, factor. Cancel everything out. Whatever doesn't cancel out, you're going to find the limit of that. And then once you find the limits, then, to find the limit, you're going to use the direct substitution just like you did for the easier part.